I'm so excited to be here. And I look forward to joining here officially this July. And I guess this is a nice chance to do a self-introduction. So I chose one direction that I'm currently most interested in to present a few pieces of my work. And to begin, I wanted to place my research more in the context of science. And I wanted to make an analogy to biologists. So they use microscopes to observe cells. And the toolkit is the microscope they use, and the object for study is the cells. And for me, I am a computer scientist by training. So the toolkit I'll be using would be computation. And what I will be observing would be divided into two parts. One is language. And in this case, using computation to deal with language is also sometimes referred to as computational linguistics. And another object I study would be language models. So in this case, I would pitch it as the sciences of language models to understand better the recently popular, powerful language models that people create but don't understand very well. And recall a little bit about this talk is about computational multilingualism. So I won't be formally defining the concept of computational multilingualism, but you can just understand its meaning as the combination of whatever that comes into your mind after looking at these two words. So it's anything about both computation and about multilingual. And so putting computational multilingualism as the theme. So the first part here would be the study that using computation to process multiple languages. And the second part would be to use computation to look at multilingual models and to better understand them. So for this, I will be using this as the outline of this talk. And for the first part, I will be presenting our work on bilingual lexicon induction, which is a joint work with my research mentors at Meta, Luke Zittelmoyer and Sida Wang. So in this part, we ask a research question like, how much translations automatically exists in monolingual corpora? Or to be translated into a more understandable version, can we do unsupervised machine translation? So we look at a relaxed version of that, where we typically, we basically just care about how many mutually translatable word pairs. So we focus on lexical semantics, and how many mutually translatable word pairs can we find given only monolingual corpora? That is to say, we don't look at parallel sentences which share the same meanings in different languages. We only look monolingual corpora. And probably optionally also a small seed lexicon. So here is an example of a seed lexicon to show the complexity of this task that is called bilingual lexicon induction. So on the left-hand side, there's English, on the right-hand side, Spanish. So we know that the word bank in English has at least two senses. One is the river bank, which translates to Spanish orilla. And one is the financial institution, which translates to Spanish banco. But actually, the sense of riverbank can be also translated to English from Spanish into other English words, such as shore or coast. And this many-to-one mapping from both sides to each other just showcases the difficulty of this task. And we still lack of a very good model to extract bilingual lexicon. And a little bit background about our approach. So here, there emerges to be very many pre-trained multilingual language models. The x-axis is the time from November 18th to November 2020, and the figure is directly borrowed from Sebastian Ruder. And the y-axis is the amount of corpora that is not English using the training process. So as we can see, most of the so-called or claimed multilingual language models are strongly biased towards English, which is in line with Verit's talk. But there are indeed a few of them, but generally the overall sense in multilingual community would be these models are generally performing less well on English tasks than the models below. But anyway, let's just assume we have a fairly performing multilingual language models, and they have some very exciting abilities already, although they are not perfect. So one exciting ability is we can encode the sentences with these pre-trained language models to a semantic vector space. So in this vector space, sentences with similar meanings are closer, whereas sentences with very different meanings are far away from each other, regardless of their language or writing system. So think about, you have a sentence in English and you have a translated sentence in, for example, Russian or Mandarin Chinese, which is in different writing systems. They are encoded into very close vectors in the shared vector space. And there are, of course, a few hypotheses of this amazing ability that's not actually expected. And a few hypotheses about reasons are the existence of code switching data or shared vocabularies, for example, English and French, English and German. These language pairs have a lot of shared vocabulary and also borrowed words or loaned words, etc. But no matter what the reason is, the fact is these language models or these multilingual language models have impressive ability. So what we can do is to encode the sentences and retrieve so-called pseudo bytext in the vector space. So by bytext, we typically mean the parallel mutually translatable sentences. By pseudo bytext, we mean sentences in different languages with similar semantics, but not necessarily to be exactly the same. And here's another very exciting ability of these large language models. So taking a pre-trained multilingual model as an encoder, what we can further do is to obtain a high quality cross-lingual word aligner given the bytext or pseudo bytext. So suppose we have a pair of English and German sentences here. What we can do in terms of obtaining the word alignment between these two sentences would be to encode these two sentences with the pre-trained multilingual model into the vector space and obtain the cosine similarity. And here, lighter colors shows higher similarity. And given this matrix, we select the horizontal and vertical argmax as the word alignment and output it as results. And this excitingly just outperforms previous approaches with supervised bytext. And the credit should go to Sabet et al. That is called SimAligner. There's a model here. And another note is the tokens in practice are typically subwords. So this enables the possibility of many-to-one alignment in terms of aligning the sentences in different languages. And again, the exciting part is no supervision here is required anyway. So given these two facts that we don't yet understand very well, what we did is to first retrieve a few pairs of pseudo bytext and then align them with a pre-trained multilingual bytext aligner and extract a few sort of statistics from the alignment. So the features, the example features we consider in this work would be something like this. So for a bilingual pair, X, S, and T, so we calculate the co-occurrence of the two pairs. So for example, das and ist would be, das and this, the co-occurrence would be 1 because it's only appearing here, or guten and morning is also 1, although they are not aligned, but this and this appears in the same pair of bytext. And similarly, we consider the features like aligned 1-to-1, that is how many times S and T are matched in 1-to-1 alignment. And this time, guten and morning are considered as 0 because they are never aligned. Or alignment 1-to-many, which handles this kind of cases that the German word danke is aligned to two English words, which are saying thank you, thank and you. And additional features we consider include cosine similarity, inner product, and whatever we can come into our mind. And what we do next is very simple, that is concatenate all these features into a feature vector. and do weakly supervised induction. So actually in the paper, we also show fully unsupervised induction, but the weakly supervised induction results are more impressive. So that's why I'm showing it here. The setting of weakly supervised induction is given an optionally available lexicon. So what we do is to extract the positive and negative examples. The positive examples, of course, are the pairs existing in the lexicon, and the negative pairs are those not, but with the co-occurrence larger than 0 to avoid too many negative examples. And the model we employ is basically to input the concatenation of the statistic features into a multi-layer perceptron and predict the probability of a pair of S and T to be in the lexicon. And the loss is simply the negative log likelihood, or to maximize their log likelihood. And here's a quick look of the results. And we use F1 score to measure the performance, which is the harmonic mean between the precision recall, between the predicted and the ground truth lexicon. And the results below would be averaged across 12 language pairs, that is German to French, and also French to German reversed, and for also for all these 6 language pairs mentioned here. And the highlight is the best BUCC refers to the best performing system in the BUCC 2020 shared task here, which is the data we use. And VacMap is the previous state of the art of the task of lexicon induction. And Wikimatrix is using exactly the same method, but supervised by text, that is humanly labeled by text. But actually, our unsupervised by text model are extracting the statistics from unsupervised by text perform the best. So this is strong evidence to say, okay, these kind of bilingual lexicon or unsupervised word translation do exist in some way in the language and in the monolingual corpora. And what we only need to do is to employ the correct way to extract them. And large language models probably just provide the correct way. And by further looking the false positive, so-called false positive cases that does not exist in the ground truth, but predicted by our model. Here are our results. We show the cases for English and Chinese, because I am a Chinese native speaker. So if you don't understand, you can just trust me. So all of them are judged by the metric as false positive, but looks good to me. So this is to say, we probably need a better benchmark for this task instead of using this benchmark to chase for higher performance. And even for the previous state of the art, many of the so-called false positive pairs are actually correct. So this is another evidence that the current benchmark probably needs some improvement. And here are a quick takeaways. So higher performance on this task is probably not very useful in terms of improving the state-of-the-art machine translation model, but actually helps answer our questions, how much translation exists in the monolingual corpora from a scientific perspective of view, or can we do unsupervised machine translations? And the answer is probably we can, in a relaxed, weaker sense. A large portion of word level translations at least exist in the corpora, and we need to extract them properly. And another quick takeaway is we use contextualized representations a lot in this work. Although this task, bilingual lexicon induction, is a seemingly word level or only lexicon or non-contextual task, the contextual representations is still helpful. So probably just look at those seemingly irrelevant things when delving into your own research is a good idea. And also the simple, as a byproduct, the simple multi-layer perceptron with statistical feature approach also improves the state of the art for word alignment. Yeah, so this is the first part. And the second part, where we switch the object to be observed to be multilingual models. So we still use computation, and we focused on the task of mathematical reasoning in the multilingual setting. And this is a joint work with Miraj Susgun from Stanford during our internship at Google, and with, of course, a lot of other amazing Google folks. And the research question we asked is, how well can the language models perform on reasoning with different languages, specifically focusing on math reasoning? And in terms of data set contribution, we extend the grade school math 8K data set to a multilingual setting. We call it Multilingual Grade School Math, or MGSM benchmark. It covers Bengali, Mandarin Chinese, French, German, Japanese, Russian, Spanish, Swahili, Telugu, and Thai, ordered in alphabetical, with pretty high translation quality, because Google hired expert translators to translate these problems. And to give you a quick glance, so here's an examples of what exists in the MGSM dataset. So this is an example that exists in the GSM 8K dataset, and this is an MGSM example. So basically, just to translate everything from top to bottom results in our multilingual dataset. We focus on chain of thought reasoning, and I'm now going to present two sets of experiments. So the first experiment, we aim to compare English versus native chain of thoughts to solve a problem in a particular language. So for native chain of thought, I'm still using German as an example. So we are shown with a German question, and this is a German chain of thought answer. And now what we do is to present the German answer, to present the German question of interest, and then to expect the model generate the corresponding German answer. This makes sense because the GPT-2 paper originally discovers that these large language models have the pattern following ability. If they show a few examples like this, they will just follow the examples to perform so-called reasoning, or at least in a very superficial form. And in terms of English chain of thought, what we do is similar, but instead, given the German question, we let the model to answer in English. We prompt the model to answer in English. And here's the quick results. As we can see, the problem solution accuracy on MGSM on both GPT-3, which are the first two bars, and the PaLM, which are the second two bars in each group, English solution is generally outperforming native solution, except for, I think, Thai with PaLM. So this is actually not very intuitive, because we are doing code switching between the question and answer. But we do have a hypothesis about the reason that pending test, which is to train a very good generator in some specific language, we need a lot of training corpora. But to train to understand some specific language, the required corpora size might be much smaller. And the key takeaway of this experiment is probably English as the chain of thought solution language generally perform well. And if you are targeting on some specific task for multilingual settings, you probably want to try English solution anyway. And of course, this is also relevant to the cultural bias or English bias mentioned in various talk. And the second experiment is focusing on English versus multilingual exemplars. So now we're doing few-shot exemplars as the prompt. So the English-only exemplars would be showing an English question, English step as the answer, and 5 more English examples in the same format. And now we are interested in answering a question that is not in English, or that has no existing example solution available. So here we still use German as an example. But instead, what we can do is to diversify the exemplars. So in contrast, what we do is to show an English question, English answer, and another 5 examples that has the questions in different languages, but solutions are all in English. As we previously found, English solutions is generally good. And finally, we still put the question of interest here and expect it to output some English answer. And the result is here. So in the first bar of each section is the English only exemplar performance, and the second bar is the multilingual exemplar performance. And actually, multilingual exemplars work very well, except on English itself. So this is also sort of expected. And it's more impressive that we use the prompt exemplars in English for the high resource languages, which is the first 6 shown in this, the left 6 shown in this plot. But actually, the languages of Thai, Telugu, and Bengali doesn't really have a shared alphabet or writing system in terms of comparing to the exemplar 6 languages. And also, even Japanese, it only have a set of shared vocabulary with Chinese. So we observed, surprisingly, the improvement of multilingual exemplars on these no overlapped language with the multilingual exemplars. The reason we hypothesis is that the prompting in multilingual, prompting with multilingual exemplars just activates some external multilingual reasoning neurons, but this is still pending rigorous assessment. And a little bit about the future work of, or what's next that I'm interested in. So I will be show this by a few examples that exist in psycholinguistic study. So the first one is people use different prepositions to describe the same spatial relations. So here's a quick example. I will use English, Spanish, and Japanese as the 3 representative languages. So in this case, English would use over to describe the relation between the coin and the coin bank, and use on to describe this black stuff and the desk, and to use in to describe the golden fish or black fish or whatever, and the fish pot. But in Spanish, the second 2 relations are described within the same preposition. However, in Japanese, the first 2 relations are described in the same preposition. So actually, for these interesting phenomena, corpus, computation, and also large language models, or generally language models, provide some new toolkits for us to better discover them systematically and understand and test these phenomena. And another thing is, language may also affect how humans view the world. This is either the stronger or weaker version of Sapir-Whorf hypothesis. So a quick example is like this. If the participant would be initially facing some scenarios like this, and then they are turned 180 degrees around and asked to position the animals on the table in the same way as before. So this is actually ambiguous. So if you are a 10-9 native speaker, you'll be favoriting this absolute recall. So that is to say, this fish is on top, and to keep the absolute relations of whatever animals as before. But if you are a Dutch native speaker, you probably reconstruct it like this. That is basically focusing on the relevant spatial relations of the object that's facing you. So I'm very interested to investigate the questions like, do language models trained on these languages have same inductive biases, Or if not, what else factors shape people to think like this? And also, can we explain the language model behaviors with machine learning theory and or interpretability techniques to find the neurons that encode these kind of inductive biases? And also, can the results about the machines or the large language models shed light on explaining human language acquisition? And a little bit ambitiously or a little bit vaguely, human experiments are very expensive. The language models are, to some extent, much cheaper to perform experiments on. So the experiments on the faithful large language models, that is in the sense of reconstruct human behaviors, may even serve as, I call it, pilot study of human experiments. So when you are doing human experiments, you do pilot study on the small scale of data and participant. So if you have 1,000 hypotheses to test, and you would like to find one or two that is the most promising for you to work on, you probably can test first on language models before conducting the first round of pilot study on humans. So I really envision the future that we use computation, we as computer scientists use computation plus X, maybe some experimental toolkit in psycholinguistics or psychology and cognitive sciences and also linguistics to explore something interesting that is including but not limited to the object like language or language models or whatever else. All right, thanks. I'm happy to take questions.
Great talk. I like near the end, you're talking about your future work and you're talking a bit about the differences between prepositions in different languages. You mentioned English and Spanish. And my understanding is English and Spanish also differ in terms of like the verb phrase structures.
Yes.
And it can make the attribution of cause or desire different in those two languages.
Yeah.
Are you thinking of also making the same kind of work you intend to do with prepositions also to apply it to verb phrases and other kinds of constructions?
Yes, I think so. So prepositions are just the examples to show the difference between these languages. And of course, in terms of typology difference, the most prominent one would be the difference in terms of word orders, subject, verb, and object. You can imagine there are 3 permutation orders, potential orders, and actually people are favoring some of them. And of course, there are already a lot of theories trying to explain this, but I guess in the future, I'm very interested in to ground them into the real world and use more data and probably multiple modalities to explain these phenomena.
Isn't it quickly follow up? Because like in English, we'd say something like, you know, the person knocked over the vase or the boat floated into the cave. Whereas in Spanish, word by word, we'd say things like the boat entered the cave while floating. Oh. Right? Or the vase was knocked off and the person was there. So the construction kind of takes the emphasis off of the active agent, supposedly. So like if you wanted to ask questions about a language model, like who caused the boat to go in or was going into the cave on purpose or something, apparently that would be like a difference between those languages.
Yeah, interesting. Yeah, I also believe there's definitely more work to do to construct the test suite in terms of syntax for multiple languages. And most of the existing work are focusing on English exclusively. Yeah, and I totally agree with you.